So now that we have a basic framework for how statistics operates in chemical analysis, or just analysis of a number of measured values in general, one of the key questions that we can start to answer, which becomes really valuable in analytical chemistry, is how do we determine if two sets of measurements or two sets of data are statistically different? Or in other words, say, I did a measurement of lead in drinking water 10 times, and you did a measurement of lead in drinking water 10 times. And my average, which I'll write out as X bar 1, was maybe 2 parts per million. And yours, which I'll write out as X bar 2, was 2.2 parts per million. They're never going to be the same because of random error. If you've learned anything so far, hopefully you know that, right? Random error is going to tell us that we're never going to get the same numbers. But are these numbers statistically different, meaning they actually come from two separate distributions? It's not even part of the population, right? Because what we're actually asking is this small sample size and your small sample size, do those both come from the same mu, or population? And that's the question we need to answer with statistics. They'll never be the same, but if they're coming from the same population, then the difference that we see simply comes from the random error. It can be explained by random error. If they're statistically different, then random error cannot simply describe the difference, and there must be something else, either systematic or truly different, about those sets of measurements. That's where statistical tests of significance come in. And I've got 3 different scenarios here that I grabbed out of your book because they illustrate 3 different types of tests and lines of logic, or different situations that you find yourself in as a scientist doing several measurements. So case 1 here says that we measure a quantity, so by quantity measuring a sample several times, and you obtain an average value and a standard deviation. We need to compare our answer with an accepted answer. The average is not exactly the same as the accepted answer. So does our measured answer agree with the accepted answer within experimental error, which means within the random error that could and will be present in the universe? This is slightly different than the example I just posed, because here I am doing a measurement, maybe 10 measurements of lead in water. That may be the quantity I'm measuring several times, and I get an average value. So in this case, I get an average value is equal to something. But instead of comparing that to another person, we're comparing that to a true value, what we're calling here an accepted answer. An accepted answer is sort of codified language for essentially a true value, or as close to true as we scientists and humans are going to allow ourselves to get. And so what we're essentially comparing here are 2 values, one in which I calculated or determined, and one that is accepted. And by accepted, that might mean that it's been measured so many times before that we generally know what that value is. And that's true for like physical constants of the universe, where so many people have derived them and we've spent a lot of resources on it that we're pretty close to a true value. In that case, I'm comparing my value to the true value. Another way to generate a true value is that we have these places, which I alluded to in another video, like the National Institutes of Standards and Technology, who spend a lot of time and energy producing true values or close to true values for lots of different measurements. You can go on to the NIST website and you can buy these things called SRMs, which stand for Standard Reference Materials. And as the sort of name implies, standard reference material means that NIST has like a peach leaf where they've analyzed with great accuracy and precision exactly how much, say, phosphorus and potassium and aluminum are there. And so if you are in the lab and you are interested in measuring a certain quantity of phosphorus in your own peach leaves, say in your own backyard, and you do that analysis, one way to check if your method is good is to go buy one of these SRM peach leaves from NIST, measure it, and compare your value to what NIST obtained. And you would do that through one of these significance tests that we'll talk about. A separate case here is if you measure a quantity multiple times by 2 different methods that give 2 different answers. So in that case, you have, say, a sample. So it's just a sample like this, and you've got two different methods. Maybe you're measuring lead in drinking water again, and you're measuring the same exact sample, but you're doing one by ICP and one by a sensor, and you generate two data sets. How do we know statistically if my sensor is producing a different value than the ICP-AS? So it's statistically different. That's a different case there because we're talking about the same sample being measured by two methods, which is different than the first case where we're talking about several samples being measured by one method and then being compared to a true value. Both of these are unique statistical cases. And the third case is we've got sample 1, which is measured once by method 1 and once by method 2. They do not give exactly the same result. Then a different sample determined to be number 2 is measured once by method 1 and once by method 2. And again, the results are not exactly equal to each other. So the procedure is repeated for n different samples. So you do that with a bunch of different samples. So we sort of have 3 different scenarios in which we have different tests of significance. Okay, so with statistical tests of significance, there's lots, as you can see, depending on the case or the situation. And so I drafted a decision tree that I think can be helpful in concluding what test to do, along with the equation, though it's often that in this class and going forward, I'm going to highly recommend that you don't do these things by hand, that you do these things with Excel as a spreadsheet, because it's much, much faster. But I have them included here. So this handout will be on Canvas. It'll be made available to you, and you can use this on any assessment at all, so exams or quizzes or whatever. And what I have is you start the decision tree at the top where it says are means significantly different, right? And that's the question. So you've got 2 samples of data, you get some averages for both, and you want to know, are they different? So that's your starting point. You move down, it says what is the nature of data / comparison. You go down one and it goes to outlier data. So before you even get to test of significance, you have to determine if you've got any outliers in your data set. Outliers are data that are quite a bit removed from what the true value is. Sometimes you can just look at it and say that piece of data doesn't make any sense. But it's not good practice as a scientist to just strike that data from your data set without evaluating whether or not it actually falls within the normal distribution of your system, given what your standard deviation and mean or average are for your set of data. And so there's 2 different ways to do that. You can either do a Q-test or a Grubs test. So a Q-test takes the questionable data point. So if you've got a data set that's like 10 different measurements and you see one of them looks weird, you would take that value, the questionable value, and then subtract from it the next nearest value in that set of 10 numbers. Whatever one is closest to it in the positive or negative direction, you subtract that. And then you take and divide into that the difference between the maximum value and the minimum value. That gives you a value called the Q-calc. And then there's a table that's called the Q table, where you go into and you look up the Q table for your condition. I'll show you that here in a second. So Q table looks something like this. This comes straight out of your textbook. Some Q tables can be really large and include a lot more information because they often represent different levels of confidence. Confidence being how confident you are that that data is in fact part of the data set. And so this is typically Q tests are done at 90% confidence, which is why your textbook has only the 90% confidence input here. And then here we have the number of observations. So how many measurements did you do? So again, the expression for determining the calculated Q value is going to be the questionable value minus the nearest divided by the range, max versus min. And you would reject that data point, meaning you would strike it from your data set if the calculated value was in excess of Q table. So if you did 10 measurements, you'd look over at the Q table, you'd say, okay, 0.41 is my value at 90% confidence. And if your calculated value was greater than 0.41, you would statistically say that that data point is not part of the population and must be due to some systematic error that you can remove from your calculation. So you would remove that data. Similarly, the Grubs test, or sometimes called the G test, is really similar. Again, it's questionable data point minus the average in this case, that's x bar, divided by the standard deviation gives you a calculated G value. And that calculated G value, again, the criterion for rejection is if the calculated is greater than the table value, then we reject it. And so in this case, instead of a Q table, you would be given a G table. So this is always the first waypoint when treating data for statistical significance, because of course if you include an outlier piece of data, it shouldn't be there, that's going to throw off your average and standard deviation, which are critical pieces of information when we're trying to compare their statistical significance. So all data sets in this class, the first thing you're going to want to do is vet them by evaluating those values through Q's or Grubs test. You can do those. These are really easy formulas to just set up in Excel, but Excel also in the data analysis package has a Q or a Grubs test available to you, so you can actually run your data through that too if that's useful. You'll just have to look up how to do it for your specific version of Excel. Okay, so once you've sort of dealt with any outlier data, and I'll say no here because you've come back through here and you've tossed it, you've got three sets of criteria which are similar to the three cases that I brought up in the earlier part of the video. Are you comparing your mean value to a known value? So that's like comparing to a standard reference material. So you've got a mu, you've got a population average or mean that you're comparing your sample average to. That would, if you follow that route, you say yes, then you're going to do that with what's called a confidence interval. And I'll talk about that here in a second. Here's the expression for determining a confidence interval and the criteria for evaluating whether it is significant. It says it's significant if X that you compute or your value is outside the confidence interval that you make. So if your value is outside, or if the true value is outside the confidence interval, then the mu is outside the confidence interval, doesn't lie within that range, then it's statistically significant in its difference. It's actually different. Okay, so if we go down this middle path, if you're comparing two sets of measurements, yes, are standard deviations different? Meaning, are they statistically different? You first have to answer that question, which requires you to do this thing called an F test. So an F test is really simple. It's just if you've got two sets of data, so you're trying to compare two sets of measurements, and you want to know if the means are different. Before you can test if the means are different, you actually have to figure out if the standard deviations are different. To figure out if the standard deviations are different, you run the F test. The F test is really basic. It's just a ratio. So you take the standard deviation of the first data set squared divided by the standard deviation of the second data set squared. So in this case, maybe it's two sets of measurements, meaning you measured my lab measured lead in drinking water, and a lab in Flint, Michigan measured lead in drinking water, and we wanted to compare our two data sets. We both have averages, we both have standard deviations. We compare the standard deviations first through the F test. We get this F calc value, so the calculated F statistic, and it becomes, again, significantly different if the calculated value is greater than the F table value. So let me show you the F table. F table from your textbook looks like this. So you can see at the top it says critical values of F. That's the first standard deviation squared over the second standard deviation squared. And this is all at 95% confidence. That's what this table is generated at. And what you can see is sort of a matrix or a grid where you have on the top the degrees of freedom for the first standard deviation, and on the left the degrees of freedom of the second standard deviation. Degrees of freedom in statistics means whatever your the number of samples that you had in that sample. So let's see if I can draw here. Let's grab that. So for your first set of samples, maybe you did this 10 times, n equals 10. The degrees of freedom is going to be n minus 1. And similarly, say for the second set of data, again, maybe we measured this, I don't know, 8 times. Say the lab in Flint measured their samples 8 times. Then our degrees of freedom are going to be n minus 1. So what we'll do is go to 9 degrees of freedom on this axis and 7 degrees of freedom on this axis, and we'll go over and get a value of 3.68. So our F statistic here is going to be 3.68. That's our F table. And remember that if F calc is greater than F table, then the standard deviations in this case are statistically significant in their difference. So what does that mean when we're back to this table? Well, if the answer is yes, they are statistically significant in their difference, then we're going to do a t-test, but it's going to be called a two-sample t-test with non-pooled standard deviations. And if the result of the F-test is negative, meaning they're not different, meaning those standard deviations are actually coming from the same population, not different populations, then we can combine those standard deviation. We call that a pooled two-sample t-test. So there are two different t-tests. You can see the equations are different. They're slightly different depending on whether you're doing pooled or non-pooled standard deviations. You can do these by hand, but as I mentioned, you can also select this in as two different types of t-tests in Excel, and these equations will be implicit in that calculation. Okay, so the last example here, or case, would be comparing two methods on a single set of samples. So what that means is, say I have 5 different water samples, all with different measures of lead in them. So 5 samples that we took from, say, you all in the class, right? I had you bring them in. And we ran those exact same 5 samples on one instrument and got a set of data for the concentration of lead. And then we ran the exact same set of samples on a different instrument in the department. And so in this case, we're taking literally the same samples and we're measuring those with 2 different methods, which is different than our previous case where we're actually comparing 2 totally different sets of measurements, meaning the samples were not identical. They're just completely different sets. So in this third case, when it's the same set of samples just measured 2 different ways, we use what's called a paired t-test, which has an expression that looks like this. So we're going to do a couple examples here.